Hi, everyone. Thank you for working so hard to learn today, spending a full day in classes and sticking late into the day to spend this time with me. So I very much appreciate the opportunity to speak with you. Um, my name's Kevin Klein. I have been in the industry for quite a long time, I've been working as a data person since the mid 80s when I started to work on a project using Oracle. I was the database jockey, a database person for a big project in which we built the water recycling system in the International Space Station. And so I was working at NASA at the time and worked with Oracle for a while afterwards and switched to SQL Server before it was a Windows product. So it was still wasn't quite a Sybase product, but it was not yet fully a Microsoft product because they hadn't yet released Windows. So that was around 1994. Over the years, I've written many books, been a Microsoft MVP for quite a long time. And you can see my contact information here, Facebook, Twitter, LinkedIn, all social media is K.E. Klein. I would be thrilled if you would connect. You can also reach me via email at kevin.klein. And I'm not sure if this is of interest to any of you, but I'm 1/4 Italian. My grandfather, his name was Cassetti, Thomas Cassetti, and his father was from northern Italy, and so they moved over to the U.S. In the 1920s or so. So I have a lot of very fond memories of my grandfather and I playing, and I can remember a few words of Italian. We would play hide and seek a lot, and he would walk around in the house while I was hiding, and he would say, "Dove sono, Kevin? Where are you?" I guess is what that meant. And evidently, I could speak a little bit better Italian back then because I was always saying, "Parlo adagio, Grandpa. Speak slower. You're going too fast for me." So yeah, I have a very great amount of affection for Italy and Italians. So also a quick word of thanks to all of the sponsors and partners for the event. It couldn't be done without them. So to all of the different partners listed here, thank you. And it means a lot to the community of SQL Server people as well. So what will we talk about today? Well, the intention of this session, when I first started it long ago, was to help my developers understand what happens behind the scenes in SQL Server when the code they have written is sent to be executed by the SQL Server engine. And so they knew that something happened, right? They would send a query and magic would happen in this black box we call SQL Server, and it would return results to them. But they didn't really understand any of the operations that happen within SQL Server. So this session was intended to guide them through that whole process so that they could tell, as they were writing their code, whether it would perform well or whether it was likely to perform very poorly, because so much performance with SQL statements depends a lot on how you've written the SQL statements or how you've constructed your stored procedure or different things like that. But in the process, they had a lot of questions. And so as time went on, I've added more to the presentations just to kind of flesh out, to give them those developers a fuller sense of what it is to be doing work in SQL Server. So what we're actually going to do is the first time I wrote the presentation, I just gave them lots and lots of facts about all of the different stages, all of the different architectural components within SQL Server. And slides full of bullet points like this tend to be very hard, at least for me, to remember. And so what I decided to do was change it into an analogy, as kind of a narrative story, as if a character is walking through a neighborhood, and each of the architectural components are different things that they see as they walk through the neighborhood. By the time they come to the very end of the neighborhood, it's as if they have completed a SQL query. So that's why you see these references to neighborhood here. That's the internals of SQL Server. And so one of the questions I got after I first started to teach developers on my team about SQL Server is they would say, wait a minute, you've told me a lot about things like the SQL Server parser and the binder and the simplifier, but why do we even do all of those things in the first place? So the first question to answer is, what is the overriding set of principles that governs what SQL Server does? Why does SQL Server do things the way it does? And the answer to that is an acronym, ACID. And ACID describes the ways that not just SQL Server, but all relational databases process transactions. So if you've ever used Oracle, PostgreSQL, you've used Sybase or DB2, if you've used MySQL using the NODB engine, then all of those are all governed by the ACID properties of transactions. And the reason for that was relational databases were created and designed to fix many of the problems that had existed prior to that era, that all of those mainframes from the 60s and 70s doing their batch processing would inject into the process. They had lots of problems and they would break in lots of ways. And, you know, when you think about data processing in the 60s and 70s, in fact, you know, we didn't call it information technology then, we called it data processing. That just meant do what accountants do and do what some scientists and mathematicians do, just do it really fast. And as I mentioned, it was all mainframe, it was all batch mode. And so what the accountants do is handle money. And if you lose track of people's money, which mainframes would do all the time back then, they get really angry. You know, they'll burn down your house if they find out that you're the person responsible for that. So enter the ACID property of transactions. What we want to make sure is we don't make any mistakes like the mainframe era made. So the first characteristic of a transaction had to be that it was atomic. And what we mean by that is it does one and only one thing. When you issue a command in SQL to a relational database, it can only insert data if it's an insert command. It can't also change data. You can't use an update statement to delete data. Different kinds of characteristics like that. Each statement needs to be unique and fully distinct to itself. That's the first thing. The second thing was that your processing needs to be consistent. And this sounds so elementary, but in the mainframe days, it was not uncommon for a batch process, when run at one time of the day, could give you very different output as opposed to running at a different time of the day. So with a relational database, we wanted to be sure that every time you ran a particular set of code, it would behave in exactly the same way. Doesn't sound crazy to me, but it was correcting a problem from the previous era. I, in this acronym, means that every transaction must be isolated. In fact, this is why we have locking and blocking in relational databases. All of them, Oracle, Postgres, and so forth, they all have this. And that's because we need for that money, initially, again, the idea was money, although we use it for much more now. No one else can tamper with that until you have completely finished any write operations, ones in which you're changing data. Those have to be completely finished before someone else can get access to those records and make writes of their own. And then finally, durable, okay? And so one of the big problems they had on mainframes was that there could be a lot of work in flight, and there would be some kind of outage, like a lightning bolt hits the data center. And all of that work that had been in flight might be partially done. So a certain number of people might have had their transactions processed, while the other half of the the people in that batch didn't. And it was extremely difficult to recover from that kind of situation. And so the banks and financial houses would lose money every time these things happen because they might possibly overpay some people or they might underpay others. It was a massive issue. And if you look at these different characteristics of transactions, when you begin to consider all the different architectural components inside of SQL Server, you realize that each level deeper we go is more overhead on the relational system. So atomic, that's very easy. That's kind of parser level stuff. Consistency is also just simple characteristics of the system and the parser and the binder and the simplifier components. Isolation, as I mentioned, is the whole locking and blocking engine. That's a pretty big, pretty overhead heavy part of SQL Server. And then finally, durability, that's all of the transaction log system. In fact, you don't have to answer these characteristics in identical ways. So different databases, for example, Oracle has two methods for, or two architectural components for durability. It's the archive log and the redo log in Oracle. But on SQL Server and on Sybase, we have just the transaction log is how that works. So we have all of these characteristics that we need to support. That's not all, though. There's other reasons why we have a lot of architectural components in SQL Server. For example, lots of things are built into SQL Server to just simply make it faster and more scalable. There are certain things done to maximize hardware. For example, many of the smaller architectural components are things like log buffers. And when we added log buffers to SQL Server, that was because transaction logs on spinning hard disks were really slow. And so we'd build a little buffer so that we could make sure that those disks got spun out completely. And then we would push all of the data out at one time. And then there's quite a few competitive features that are added simply because Oracle or somebody else did something cool, and we need to make sure that we answer that inside of our relational database. Now, I want you to keep in mind that there's a lot of these non-relational databases out there, MongoDB and Cassandra and different ones like that, and they are popular, but they are not built at all on this idea of the ACID properties of transactions. They are built on something called the CAP theorem. And with the CAP theorem, we are looking at consistency, availability, and partitionability. And in this case, partitionability means the ability to scale out across hundreds or thousands of nodes. But with each of the different major NoSQL databases that you might look at using, you only get to choose two of those three characteristics. And again, when you look at it historically, this is a situation where these NoSQL databases were designed to fix certain problems of their era, which was, you think of Yahoo and LinkedIn and Facebook, who invented these different NoSQL databases. They were all about global scalability and not so much about really, really important things like money, handling money. So, if you posted a picture of your cat to show, to your cousin who lives in Paris, let's say, then that doesn't have to be immediately made consistent throughout the systems. In fact, most NoSQL databases don't have what we call consistency. They have a variation they call eventually consistent, because it'll get posted eventually. Everybody around the world will be able to see this at some point, but it's not intended to be immediately consistent or immediately available and readable, because it wasn't designed to do that in the first place. Okay, so now what we're going to do is we are going to take a walk through the internals of SQL Server, its architectural components. And as I mentioned, I wanted this to be more of a narrative. And so So I decided to use this character, Dr. Sheldon Cooper. Most people have seen an episode or two of The Big Bang Theory, and so this is a familiar character. And so think of Sheldon is an expression of a query, right? He's actually a query. But what we're going to do is we have this neighborhood. So imagine Sheldon has gone to a conference, and he's going to speak at some big theoretical physics conference, and it's in a city like New York, okay? And so here he is at the start. He's gonna, again, he's a query. But what he has to do is to get through all of these different buildings all the way back to completing the transaction, okay? So each of these different objects are a building on his expedition through the city to answer a query. And where we start here, he's stepping out of the hotel, okay? And everything along the top, by the way, these are tiny little structures, architecturally speaking. They're very, very small. The interactions with them is very brief. So think of it if you were walking, like I'm thinking of Manhattan, and there are vendors who have push carts and they sell hot dogs and they sell other kinds of food. That would be these along the top. You could just stop and say hello and then move on. That's because everything along the top here is all part of what we call the relational engine, okay? Everything that happens there happens in CPU and memory. It doesn't interact with the I/O subsystem at all. And then over here on the right side, these little buildings are just a tiny bit bigger, but still, you can tell by the color, they're related in the sense that they are still very, very small. So another example of that kind of building we have in the USA, in Manhattan, might be a little flower kiosk. So there's a little roof, there's some doors, but every morning the vendor opens the doors, sets out flowers, and you can pay at a little cash register there. Or maybe it's a newsstand and there's a bunch of magazines, you can buy a soda. So these are also very small, very brief interactions with the internals inside a SQL Server. That's all the relational engine. Then we have these different colored buildings on the bottom. This is all part of the storage engine. These are moderately large buildings. They're in Manhattan, they call these kind of buildings a walk-up, meaning it's tall, it has many floors, but it doesn't have an elevator. So it's not going to be 12 stories tall because you can't get your furniture up there. It's like 4 stories tall. So these are kind of resource intensive. In fact, there's a stoplight here at the transaction manager. You have to, that'll stop traffic. But then we have the high-rise buildings, and those are right here in the middle. We have the memory, and we have the files, the different file systems. The file system of our database files, our transaction log files, okay? They kind of dominate the landscape. So when Sheldon decides to go into the city, and by the way, this is the same on any platform for SQL Server. If you're on premises, if you're in the cloud with Azure SQL Database, Azure SQL Managed Instance, works the same everywhere. What happens is Sheldon leaves his hotel, and that's the kind of the start of everything, right? You write your query and you say execute. And so what SQL Server does is it engages something called the SQL networking interface. And it takes the code, the SQL statement, and it uses something called TDS, the tabular data stream, and it puts the TDS packets into whatever your network interface is. So in the old days, we used to use something called named pipes quite a lot. But nowadays, almost everybody is using TCP/IP. So TDS takes that code, puts it into TCP/IP packets, and then it sends it over the line, over the wire, to the next step, okay? So Sheldon sets out on his expedition, and he encounters something on the target server. It's called the SQL OS. So again, let's say he's using TCP/IP. So by default, SQL Server would pick up his query on port 1433, and then SQL OS says, aha, someone's asking a request of this SQL server. Let me give you a thread, a SPID, a system process ID. So Sheldon gets a thread, let's say 73, for example, and now he can get work done. So, and I do have a little bit more detail on how the thread management happens if you're interested in that. So then Sheldon gets to actually take a look at the parser, right? The parser, again, very tiny little building. He can check it. Oh no, I don't need a candy bar. And then he's done. But what the parser does is a few very important things. And by the way, it's sometimes called the algebraizer or algebraizer or the normalizer. So it does, at its face level, it checks the syntax. So if you were typing a select statement and you typed SEELCT, you misspelled the word, you would get a parser error and it wouldn't be able to complete that that statement properly. It'd say, oh, I don't know what you mean. It does more than that though. So it validates the syntax, but it also identifies any constants. If there's a view, then it expands that out. So what might have appeared to be a very simple query can become pretty elaborate if it turns out there's a view underneath that with lots of its own where clauses and joins and things. I mean, it then builds an initial logical parse tree. However, all of these steps across the top are designed in such a way that Sheldon could maybe take a shortcut and skip all of these neighborhoods around the outside edge. And the way SQL Server first tries to do that is it takes this initial parse tree and it says, has anyone else done something very much like this? And it checks the SQL Server plan cache. It says, okay, Sheldon has issued a query about some research, right? It says, has anyone asked this same query, maybe with a slightly different title or some other change in the variables? That's okay, it can deal with that. And if they have, what I get to do is I get to skip visiting all these other buildings. So if it does find it in the plan cache, then Sheldon pulls that query out of the plan cache and it executes it, and we get to skip binding, simplification, and optimization of the query. If, however, it's not in the plan cache, then Sheldon has to go to the next step. The next step is called the binder. And again, the binder has some very, very important characteristics and behaviors that it does. The first thing that it does is it checks to see, okay, the parser tells me that you had a properly formed query, but do you have permissions to all of those objects that you tried to query? Also, it will resolve the metadata in terms of names in the tables that you reference. So if you reference a column that doesn't exist, it's the binder that would catch that problem. It checks for data type issues. So if you have a union statement, for example, and it's a union of just one column, and the top one is an integer and the bottom one is, let's say, a date, then it'll say, okay, this union query does not work because the ordinal position of each column has to be the same data type. It also does your aggregations here. It binds the aggregations at least. And so if you have a count or a average or a sum kind of in the item list of the query, it checks those to make sure that you also have the appropriate group by statement that matches in the right way. And hey, let's make sure that this is updated properly in the plan cache. So we're building and adding details to the execution plan in the plan cache as we go along. Once that's done, Sheldon gets to move to the simplifier. And the simplifier has some very interesting abilities. When I guess I was probably in the mid 90s. It was between SQL 6.5 and 7.0. That's when we first started to see the simplifier come into action. So it's weird to think that I was actually there looking at these different techniques being added to the optimizer. But what what they started to do was in previous releases, for example, you could write a join SQL statement, or you could write a select statement that had a correlated subquery, and they returned the exact same result set. They looked very, very similar. Well, up until that time, you could write one manually and the other manually and compare them because you would almost certainly get different execution plans. However, again, I think it was around SQL 7.0, but it could have been a little bit earlier. At that time, they added the simplifier, and the simplifier, one of the first things it learned how to do was to take a correlated subquery and basically automatically transform it behind the scenes into a join statement. And so that way the optimizer didn't have to work as hard to figure out how to process your query, because now it had less choices it had to work its way through. Okay. So the simplifier does a lot of very powerful things. For example, if you have multiple joins that say the same thing, join the employee table to the manager's table, and that join appears 2 or 3 times in the query, we don't need it 3 times. It'll keep just that one join statement in there. It also does other neat things like predicate pushdown, aggregation on unique keys. Another one that's kind of cool is called contradiction detection. So let's say you had a query against a table and there was a check constraint on one of the columns, and it said that the integer value in this column has to be 75 or greater. But the query that Sheldon is running says where my column is greater than or equal to 6. Well, it would, in that case, it would know that it needs to change the parameters of the query because nothing is allowed in that table that's less than 75, or, it has to be 75 or higher. And if in fact his query actually said something like where the values equal 50, well, the optimizer knows from the check constraint that this is a complete contradiction. There can be no values at all of 50, because it has a constraint that says 75 or greater. So again, each of these steps are designed to reveal if there is an issue with the way the query is written and to cause it to fail here, now, before Sheldon has to walk all the way around these big city blocks in Manhattan. Let's save time by making it fail as early as we can if we know it's not going to work anyway if he went to all that extra work to complete this. And by the way, if you're interested, I do have example queries for all of these different behaviors. It's just that we don't have a lot of time to cover all of those with examples as well. So the simplification process yields a lot more good information for SQL Server, and it updates the little query plan thumbprint in the plan cache as it's going along. Okay. Now, this is the first step. Sheldon has reached the point of SQL Server creating a trivial plan. So trivial plans are pretty interesting. One of the things that I didn't realize about trivial plans is that they don't really even get cached into the plan cache. They will appear for just a moment into the plan cache as they are created, but then they're also immediately marked for eviction so that SQL Server can always have that space free and not experience a lot of memory pressure right there. So the trivial plan step it happens before optimization. So it really doesn't even use any of the metadata that might exist on that table. If it has indexes and things like that, it won't use it. It only uses the table and the column descriptions, which surprised me. So let's say, for example, Sheldon had written a query against a table that was it had a clustered index, no other structures at all on it. And it was also only, say, 12 records in that table. SQL Server is always going to do a clustered index scan on something that small. Conversely, if he were to do a query on a table that was a heap, and it had no other indexes. So it didn't have a non-clustered index of any kind, nor did it have a clustered index of any kind. Well, again, SQL Server would look at that and say, guess I have to do a full table scan because that's the only way to resolve that query. But again, the idea here is for SQL Server to say, you know, we're done. If I can apply these rules for a trivial plan, that means Sheldon doesn't have to go over here to any of these other steps. So we can make it very fast and can circumvent all of the long running parts of creating a query. Okay. But if it's not a trivial query, not a trivial plan, then Sheldon has to turn the corner in this neighborhood. And now it starts, the amount of work being done starts to get a lot heavier. So first thing that Sheldon needs to do is he needs to load the metadata. So up until this point, hasn't loaded statistics that are auto-created. He hasn't loaded the index statistics, the histograms. He hasn't checked the cardinality estimates, which is the number of records that SQL Server thinks it might need. And so the metadata is more than just, a lot of people who know a thing or two about SQL Server know that the metadata is the indexes and statistics, but there's more to it than that. Metadata involves all of the things that SQL Server needs to know to properly create this plan. So the execution plan might, for example, be parallelized. Well, that means you have to do a check to see how many CPUs you have to know how you can parallelize it. If you only have one CPU, you can't parallelize things. So it has to look at the physical aspects of the hardware as well. Number of CPUs and the available memory, because now it's going to try to calculate a memory grant to figure out what's the best balance of giving you enough memory to complete the query versus taking memory away from other users that are active on the system. So it pulls all of this metadata together and collects it and updates the plan in the plan cache. Then it does a look at the shape of the query. Okay, is this a big query with lots of tables referenced? If it is, then we need to spend a little time looking at the join order. And SQL Server has some costing rules built into it that say, okay, if it's just one or two tables that are going to join, well, that's very simple. Whereas if it's 16 tables that we're going to join, that's very hard. And so it tries to calculate in the best way it can what is the proper amount of time to spend reordering joins. What it is shooting for here is, let's say we have a 4-table query, and each of the tables have one clustered index and 3 non-clustered indexes. Well, SQL Server might look at that and say, okay, if I join table A to B and that pulls 1 million records, but if I join table C to D first, that eliminates a lot more records. So I don't have to carry 1 million plus 300,000 plus 30,000. What I get to do is I get to knock out 600,000 records from all these others. Let me reorder the joins so that joining table C and D together happens first, so that I don't have to carry as much memory going forward into the next steps. So then that is updated into the plan cache as well, into the plan that sits there in the plan cache. Finally, we come to the explore phases. Sometimes they're called search or probe or phase. And basically the SQL Server Query Optimizer, I'm going to talk about this a little more in a minute if you're curious, but this is where SQL Server really builds the execution plan that it's going to use. SQL Server looks for the phase 0 and phase 1, it looks at the plan shape and it tries to quickly apply some rules, some costing algorithms to make it super fast and easy to calculate. So for example, phase 0, a transactional plan, SQL Server really only wants to see one join. Maybe as much as 2 joins is possible there. The idea for a transactional plan is it's primarily the most heavily used transaction in a OLTP application where you're inserting a single record or updating a single record, just very small singleton inserts, updates, and deletes. So it says, okay, is there more than 2 tables joined here? No? all right, then I can use a phase 0 transactional plan. The quick plans have a little bit more, they have a little bit more leeway, and they have a little bit more costing options here. So this might be a plan that has lots of views in it, indexed views even. Maybe there's a chance to parallelize just a little bit. Not a lot of parallelism, but a little bit of parallelism on one of the tables. So it might choose a quick plan. And then finally, there's phase 2, a full plan. And usually that's what we're going to see most often, because most queries tend to be kind of difficult. And that's, instead of saying, okay, I've got a couple plan shapes that I can accept. That's what it does in phase 0 and phase 1. In phase 2, it says, there's too many plan shapes that this could match. So instead of trying to match to a plan shape, what I'm going to do is the inverse of that. I'm going to try to prune off entire sections of the query costing rules. I'm going to get rid of those. It's called pruning. So for example, there are a bunch of special rules in the optimizer if a query references a column that has a max data type. So if it's char max, var char max, invar char max, or var binary max, SQL Server has to do a lot of special handling for those. And so if Sheldon's query doesn't have any of those, any columns of those data type, it can look at the 7,000 costing options it has in the query engine. It can say, I can trim off those entire branches of the query options, query costing options, not look at them at all, because I know I don't have any max data types. So that's what it tries to do. And by default, it tries to make a certain number of probes to get to an answer, to build a execution plan for you quickly. Now, does that mean SQL Server is trying to give you the best execution plan? No, it's not trying to give you the best execution plan. That's because it could take a long, long time to go through all the different options and calculate them each independently. So what it tries to do instead is to give you a good enough plan. Kind of like my daughters when they're dating. I'll say, he's not good enough for you. And my daughters will be like, he is, he's good enough. Okay, well, all right. Okay, then. So it enables you to move forward and get more work done. Now, moving from this point, we have now a logical execution plan. Now SQL Server needs to turn that into physical action in which it goes and retrieves the data that you're going to read, or maybe you're going to modify. So that's when we move, after updating to the plan cache, now we move to the storage engine. And this is where physical actions are actually beginning to be performed by the query. Like it's starting to interrogate memory, what's in memory and what's in the storage subsystem. And so access methods is the part of the SQL Server engine that it's a collection of methods of keeping track of where all the data is being stored in terms of is it in memory? Is it not yet loaded in memory? How do we get to the tables we need? How do we get to the indexes we need? How do we get to the partitions that we need? So the access methods takes a look at all of the internal file system components that we have here, the transaction log, the database file, plans, the plan cache and the data cache, and possibly other parts of the cache. There's also small little sections in the cache as well. Things like sort cache and hash buckets and all the X events, for example. If you create those, then those have an item in the cache as well. So SQL Server says, okay, I need to separate this behavior between read operations, select statements, and write operations, because that impacts how SQL Server does its locking and blocking and other kinds of behaviors. So first, let's look at a select statement. If Sheldon was just doing a select statement, then the access methods would say, okay, what I need to do now is to engage the lock manager. That is one of two parts of the transaction manager. There's the lock and the log manager as parts. And this is kind of a blocking operation, right? So if the records that Sheldon wants to read are being written to by someone else in the cache, he is excluded. The other person has an exclusive lock that keeps him from getting to those records. That's the C, and the I of the isolation and the consistency kind of components of the ACID properties of transactions. So the transaction manager says, okay, where do I find this data? Let's talk to the buffer manager and find out. So the buffer manager keeps track of all of the different data that has been loaded into the caches, okay? And there's different kinds of objects that the buffer manager uses to quickly find what it needs. There's things like IAMs, which is index allocation maps. There's things like GAMs, global allocation map. You don't need to know that for the purposes of this presentation, but lots of ways that SQL Server tries to speed things up. And so the buffer manager is responsible for that. And then the buffer manager says, okay, where can I find this data? Is it even all loaded into the cache? You know, if it's a big table scan, you want to look at the whole table, it might be that there's only a fraction of the pages that you need loaded into the cache. So the buffer manager says, okay, give me access to those and those pages that I need. And if they are not in the cache, then go out to the data file, which is the biggest and slowest building out here, probably. Go to the data file, find those 8K data pages that I need, and then load them back into the cache. And once they are loaded back into the cache, that's when SQL Server can supply those 8K data pages to Sheldon. And you'll get what we call the done in process message, and you start to get your records, right? Now, it gets a little bit different though when we're doing a write operation, okay? With a write operation, the first thing that you'll notice is the execution plan in the plan cache is probably going to be much, much bigger. And the reason for that is there's a couple reasons for that. The first is that if you have any triggers on a table that you're referencing, and you're doing a write operation, an insert, update, delete, or merge statement, SQL Server has to put the logic for those triggers somewhere. So it puts it into the execution plan of your insert, let's say. So that way SQL Server, if it sees that this particular column has foreign key relationships and says, okay, for this sales record, I need to have a salesperson ID, I need to have a customer ID, I need to have product IDs. What it will do for each of those constraints is it has to do a select statement against those constraints to make sure that a product ID exists, right? That a salesperson ID exists in the sales table. So those two reasons, all the different constraints on the tables and any triggers that might exist, for insert trigger, for example, that all has to go into the write transactions execution plan. So the execution plan at a logical level was built by the optimizer. Now at a physical level, it has to, choices have to be made, decisions have to be executed upon. But remember the last letter of the word ACID is durability. That means the transaction log system. Your transactions in a relational database either have to be all the way in it, completely and fully committed to the database, or the relational database has to behave as if they didn't exist at all. And so that means what SQL Server has to do now, it has to do a lot of additional work. So whereas before it only invoked, with a select statement, it only invoked the lock manager. Yeah, we're going to get to the lock manager, but before we even do that at all, we have to engage the log manager. And again, we have traffic issues here, okay? And this can be a blocking operation. It's a stop sign under certain circumstances. What SQL Server needs to do is it needs to write this transaction and it actually writes it as a kind of as a hashed value, so you couldn't read it with a naked eye. And SQL Server is writing all the transactions serially, one after the other, from all the different users at one time. That's why having your transaction log on a really fast disk, whether that's a hard disk or a SSD, a solid state drive, that's why that choice is so important. And in fact, that's also why you'll see sessions in which they recommend that you pre-size the transaction log so that it never fills up all the way before the transaction log can be cleared by a backup operation, or if you're in simple mode, by the regular checkpoints that truncate the transaction log. If your transaction log gets completely full and there's no more room to write transactions, all write operations stop in your database. So all these users are doing their work and these different transactions are being written. And it's only at that point that the transaction is completed to the transaction log that SQL Server lets you go forward. And so at that point, the buffer manager says, okay, now that we've written that and it's fully recoverable, now I need to invoke the lock manager as we did with the select statements. And now I need to find where all the data is. If the data is in the cache, great. I can begin to work right away. But if not, it has to go to the database files and load however much data you need into the data cache. That could be a really complex proposition because you might be asking for enough data to overflow what is in the cache right now. And so somebody else has to get pushed out of the cache, evicted from the cache, in order for your data to be loaded into the cache. And then as with the select statement, now SQL Server can operate. It can do what you asked it to do on the data that is in the cache. Because these are write operations, it will like either erase or update or insert new data according to what you've asked of it. And at that point, it's still not quite done because the pages here in the cache have been changed, but they have not been changed on the database files itself. That happens through an independent process called the checkpoint process. And so the checkpoint by default happens every minute, but it can happen more frequently than that if a thread requests it of SQL Server. So it's only when the checkpoint happens that those pages that have been changed in the data cache also get pushed to the database file as well, okay? A file or files, I should say. And then finally, there's this done in process message that's given to Shelton saying, here you are, you've finished your work. And the done in process message, if you've worked from the Visual Studio Code Console or from SQL Server Management Studio, that's when you run a query and it says 14 rows affected or 353 rows affected. And that's how many rows your query brought back. So these are all the major architectural components inside of SQL Server, and it's all the internals of how it works. Now, what I want to do is drive a little bit deeper here into the caching algorithms because they're so important for SQL Server's performance. So just like what we had on the previous page, we've got our two main caches. We've got the plan cache and the data cache. And we have an allocation set aside from the total amount of Windows RAM. And like I said, there's other smaller caches too. Usually the data cache is going to be somewhere between 70 and 80% of the amount of memory that SQL Server has been granted. And the plan cache, it may float up and down as well. It might be 20 or 25% of the total amount of the cache it's been granted. That leaves another 5 or 10% for you to be used in other of those small caches. It is worth noting too that the cache manager went through a big change in SQL Server 2012. So if you're running on versions before 2012, you're much more likely to have certain kinds of memory issues. So even if you have a ton of memory on a SQL Server 2008 R2 database, let's say, you may still run into memory issues where it doesn't find enough memory, because the plan cache and the data cache back in those versions couldn't lend each other memory very well. They had hard fixed numbers for the amount of memory. So how does SQL Server keep the right stuff in the cache? Well, I'll use the plan cache as an example because it's a little bit simpler than the data cache. First of all, it uses something called an LRU algorithm. That means least recently used, and the -K actually stands for complexity. And I'll explain what the complexity is and how that works. And it relies on two processes to keep track of all of the objects in the cache and to do garbage cleanup when things are no longer needed in the cache. So let's say I have executed a new stored procedure, and it has SQL Server assigns to all code, whether that's stored procedures or ad hoc queries, it assigns two little values. One is the complexity value, and the other is the complexity countdown timer, okay? And so every minute, this process called the Lazywriter, every minute that process wakes up and takes a look at all of the objects in the cache, the plan cache. And it says, have any of you not been used since the last time I was here? So it looks at all these different objects in the cache, and if they have not been used, it will decrement the complexity countdown timer by 1, okay? It goes away, comes back a minute later, and performs the same sort of behavior. Any of these that haven't been used get decremented by 1, while those that have been used get a different behavior. Now, what do you think will happen when SQL Server Lazywriter comes back again and sees that some of these different items in the plan cache have reached 0? Well, if you're thinking it depends, you're right, because it depends is the correct answer for every technology question. What happens? Well, it depends on whether there's memory pressure or not, okay? And since 90% of the time our databases are much bigger than the amount of RAM we have for SQL Server, that would usually mean that the execution plan would get, with the lowest value there, would get evicted from cache. But that's not truly what happens. What happens is when it reaches 0, SQL Server marks a bit in the header information of the plan in the cache that the record is now ghosted. If there's not any memory pressure at this point, well, why don't we go ahead and not clean it up, not delete it out of the cache? Because someone might ask for that query soon. And so we want that reusability of our execution plans to speed up processing. So if there's not any need to force it out of cache because we don't have memory pressure, let's leave it. But if it drops below 0 and there is a lot of memory pressure, let's go ahead and have the ghost cleanup process take care of that and evict it from the cache. Meanwhile, other people are actually using these different objects in the cache. And so every time someone reuses an object, it resets the countdown timer. And so the plan, the Lazywriter, when it comes back again, some of these have been reset up to their complexity level and get to count down from there. So that's how the SQL Server system can keep a very small, easy query active in the cache for hours or days or months because it's being called hundreds of times a minute, while others, say a daily report, are so big and expensive that they get to stay in the cache for a couple days just based on how complex they are. But if no one uses them in that time, SQL Server will eventually kick them out. On the other hand, they're so big and complex, we want to keep those in the plan cache a lot longer so that SQL Server doesn't have to expend all those resources to build the execution plan, optimize it, and get it there into the cache. Now, you might ask what's different about the data cache than the plan cache. I mentioned the checkpoint process and how that fixes data and pushes it down to the database level. Aside from that, it's very, very similar to what we have in the plan cache. However, the difference is that there are actually 3 objects instead of just one kind of object. So in the plan cache, we can store executable SQL code. In the data cache, we can store non-clustered indexes independently of anything else, clustered indexes, and heaps. So there's 3 different structures that can be stored into the data cache, and SQL Server keeps different countdown timers on all of them. And those that have been least recently used are the most likely to be evicted when there's a need for that space in memory. So that's basically what I say here on this page. 2 things though, if you're a developer, and most of us are, don't forget, the key rule here is you want to manipulate as little data as necessary to complete your query. So if you had 2 versions of a query, one that said select star all the columns from my table with a where clause, that's going to consume a whole lot more of these 8K data pages across the bottom than if you needed only 3 of those columns. And so you would force other tables and indexes and so forth not to have the space that they might need in the data cache. Then on top of that, if you have indexes, then that can really help you by speeding up those queries, the select statements, and enabling you to get, instead of a full table scan, maybe just an index seek. So you only pull 3 of the pages that you need to get the answers you want, rather than 300 8K data pages, because you said select star from table without a really good where clause. The last thing I want to mention too is if you're on SQL Server 2016 Service Pack 2 or later, one of the really cool features that used to be restricted just to Enterprise Edition is now available on all editions of SQL Server, and that's called data compression. You can apply data compression to your indexes, including your clustered index, meaning your table. And there's 2 kinds, page and row. We typically recommend page compression as a default, because if you're now on that version or higher, it really doesn't cost you very much at all. The savings you get are massive, about 60% reduction in I/O, about a 60% reduction of what gets loaded into the memory. So it not only saves you storage space, but it saves you a lot of memory, gives you more room to load things into memory. And we've done extensive testing on this, and there are some exceptions to the rule. But if you have a standard kind of OLTP workload, you're going to only experience a added cost of about 0.6% CPU. So I've heard people say, no, I don't want to apply compression because we use a lot of CPU. It's usually running 60, 70% busy. Well, that data compression is going to give you an enormous amount of I/O and memory improvements at probably a very low cost. Okay. So not much time left, and I still have quite a few slides. So I'm going to head into the wrap up. What we have here, I want to get across the idea to you of let's do the math. I'm actually really impressed how quickly SQL Server can answer our queries, consider some of the things that we ask SQL Server to do. So let's assume, let's do the math on a query in which we have a 4-table join, okay? Tables A, B, C, and D. Each of those tables has a clustered index, 3 non-clustered indexes. And we're going to do joins across all 4 of those tables, okay? Not a very sophisticated query, pretty simple. So we have, per table, we have 72 physical access methods available. We could do an ordered clustered index scan or an unordered clustered index scan. We could do an ordered range scan, or also called a partial scan, or we could do an unordered range. So we have all these different things we could do. We could do it across all 4 tables. And that actually explodes the number of options enormously. However, SQL Server will be cutting these down very low to a very low number of selections at the access methods phase of the processing. So let's say we've got 72 of these per table. Then SQL Server, again, this is a more complex query. This isn't a query that has 2 tables in a single join. So it's going to try to figure out what is the best logical order for our joins to happen. Perhaps if we join table D to table C first, that eliminates hundreds of thousands more records from the result set than if we start with table A joined to table B. Again, the idea here is SQL Server wants to minimize the memory grant that it has to give to the query in order for it to execute properly. So it's trying to minimize the resources needed for the query at this phase. And that puts another 24 options onto this set of calculations. And then finally, we have certain very physical things that SQL Server might do at this level. For example, there's 3 kinds of joins that SQL Server can do. It could do a nested loop, a merge join, or a hash join. It might also need to do maybe different kinds of sorts. And if there's not enough space in cache to do your sort, it has to create a temporary table to do that sort. There's lots of things that create temporary tables. For example, anytime you have a group by statement with a halving clause, SQL Server is going to create a table in TempDB to finish that work. So after SQL Server has actually eliminated a bunch of options, we're still left with about 26,000 possible execution plans at this point. So the fact that SQL Server is able to give us a properly performing query fairly quickly is pretty impressive to me. I mean, that's a lot of different options. There's lots of other tips and tricks, though, as you go along that you learn that SQL Server, or that makes SQL Server perform poorly. So that's what I spend a lot of my time speaking on. I have lots of sessions about different things that you might do in a SQL query that causes it to not even look at an index, for example. So lots of those rules that you can learn and improve your skills as a SQL developer. So that's the life cycle of a query, and that's also all of the major internal and architectural components inside of SQL Server, the major internal processes. If you ever need help or are looking to get questions answered, there's a couple websites I recommend. Don't use Twitter, but have a Twitter account. The reason for that, the SQL community is very active on Twitter, and use a tool called tweetdeck.twitter.com. So it enables you to create lots of channels. So, if you're a fan of Milan football, you could put that channel in there. If you've decided to make all your friends angry and you're a fan of Real Madrid or something like that, you could watch a channel just for everyone tweeting about that. And in our world, the SQL world, you could say #SQL help, #SQL help. And that's a channel where people just answer questions for each other all day long. And it's really great to see how quickly answers will appear there. There's also a really good Slack community, SQLcommunity.com or .slack.com. DBA Stack Exchange is excellent, and there's lots of long form questions there, much more involved and detailed there. And then I also have my blog here. It's changed a bit recently since the company I work for was acquired by SolarWinds. But for example, I have a whole series of presentations I've done recently about how to conduct a T-SQL code review. So the idea is maybe you're the lead developer on a team, or you're a DBA and you want to check all the code, give it a smell test before it goes into production. And so I give you all kinds of scripts that help you do that sort of test. All right, so to summarize, if you've not heard of ACID, This is something that will gain you credibility points in people's minds if you are aware of how a transaction needs to be atomic, consistent, isolated, and durable. Again, the key components of the relational engine, that's the top and a little bit of the side. In the little city map for Sheldon is the parser, the binder, the simplifier, and then the query optimizer. On the bottom, the really expensive operations are the access methods, the transaction manager, and the buffer manager. And each one of those has to interact with not just memory, but also with the I/O subsystem as well, whether that's very slow hard disks or not as slow solid state disks. The key areas of the cache are the data cache and the plan cache, but there are also lots of other ones. Processes that keep the caches clean and do memory management are the Lazywriter and the Ghost cleanup process. And I'd give you some extra points too if you remember what checkpoint does. And then finally, the two key areas that you need to remember about the transaction manager, since that can bring a query to its knees and not let it go any further forward, are the lock manager, because we can have locking and blocking and deadlocking, and the transaction log manager. So those are the key things you need to remember here. So with that, I want to say thank you for your time. And if anyone has any questions, I will make myself available for questions as well.